discussion video about material relating to prime numbers, which I believe is section 4.2 in our textbooks, and strong induction, which is section 5.2 in our textbooks. So I'm actually going to start with strong induction here, but the key thing I want to do is apply this principle of what we're going to call strong induction to an important statement about prime numbers. Okay, so first, let me go over what strong induction is, and what I'd like to do is compare it with regular induction. So you'll hear me from here on out refer to mathematical induction. I might slip, if you will, and call it weak induction or regular induction. And what I'd like to do is compare this with this new technique that I'm calling strong induction. Okay, so it turns out both of these techniques are really similar. So regular, or quote-unquote weak induction, is used to prove infinitely many statements. We were calling them P of n, and that was maybe for all n in the naturals, or at the very least for all n at a certain starting point in the naturals, and beyond that starting point. Strong induction is identical here. Strong induction is also used to prove infinitely many statements, maybe for all natural numbers, or at least for all natural numbers at and beyond a starting point. Okay, so regular or weak induction has two steps, and the first step is the base case, and the second step is what we call our inductive hypothesis, or inductive step rather. And this is pretty much identical for strong induction. There's two steps. There might be a little bit of a difference here in the base case. Sometimes you'll have base cases, and you also have an inductive step. And so in terms of the structure, they both have these two steps. They're identical. But where the big difference is in this inductive step. So let me go over here in red, remind you that the inductive step was an if-then, right? The inductive step was if P of k is true, then P of k plus 1 is true. And strong induction has a different if-then for its inductive step. So for the inductive step under the strong induction technique, we don't just assume P of k is true, we also assume the previous case, P of k minus 1, the one before that. And we might as well assume that all previous cases are true. So our inductive hypothesis is different in strong induction. We're going to assume not just that P of k causes P of k plus 1 to be true, but that P of 0, P of 1, and all the way up to P of k causes P of k plus 1 to be true. So what's going on here is what we called the inductive hypothesis, P of k, right? This is the hypothesis part of this if-then, the if part. So this is our inductive hypothesis, is much different than the inductive hypothesis under strong induction. Under strong induction, we aren't just assuming the immediate predecessor case, we're assuming all previous cases as our hypothesis. This is our strong inductive hypothesis. And by the way, this is where the name comes from. We are assuming more of a hypothesis in this version, in orange, right? So the hypothesis is somehow larger, maybe more powerful, so we call it strong induction. And so the way this sounds, right, in regular induction, this inductive step would say something like, suppose P of n is true for n equal to k, and then we want to show that P of k plus 1 is true. Right? This is how we might word this part of our inductive proof. But now, if we're using strong induction, the way we would word it is like this. Suppose P of n is true for all n starting at our starting value and ending at k. And then we'd say we want to show that P of k plus 1 is true. Right, so the inductive step is very different in strong induction. Just to sort of keep this versus table going, let's compare the analogies maybe. In regular induction, I said, imagine that you have dominoes, and what you're trying to do is argue that all of these dominoes end up being knocked down, even though there might be an infinitely long string of them. So this might be your kth domino, this will be the k plus first domino. Right? And so the inductive hypothesis says, suppose you can knock down domino k, and then you want to prove that knocking down k causes k plus 1 to knock down. That's another word saying the dominoes are lined up. Right? The base case is saying there's a first domino that we can knock down. Okay, so maybe a good analogy, for strong induction is to say, well, maybe our dominoes are kind of weird. We have a little domino, and then our dominoes get bigger and heavier. And so by the time I'm at some gigantic kth domino, the k plus first domino is even bigger and heavier. And so the way I like to think about strong induction is a little bit like this. If I just knock over the kth domino, it might just tilt over, right? Sorry. It might just tilt over and lean against this heavier k plus first domino. I might knock it over, but it might not push over that big, gigantic k plus first domino. It might just lean against it. Right? Maybe this k plus 1 statement is a lot trickier. It needs more to knock it over. So rather than just having the previous domino lean on it to knock it over, what strong induction says is, well, let's use the force of all of these dominoes. They're all leaning on this one, and that will then hopefully cause it to fall. So that's sort of an analogy of strong induction. Okay, so I just want to point out a couple things before we see an example, and then we move on to prime numbers. The first thing I want to point out is strong induction, even though it sounds different and it has a different phrasing to it, especially particularly in the inductive step, it's equivalent to regular, or what I'm now calling weak induction. What do I mean by this? What I mean is that if you can prove statements using weak induction, then you get for free this technique of strong induction. Vice versa, if you assume you have the ability to use strong induction, you get for free the ability to use weak induction. So even though these feel different, and one technique feels sort of maybe more powerful than the other, it turns out they're equivalent. If you have one technique, you have the other. So this sort of begs the question, since they're equivalent, when should you use one over the other? When should we use one version over the other? And I'm going to give you an inelegant answer here. The answer I like to say is, well, try regular induction. So try weak induction. If it fails, try strong. Okay. And then another point to make, this is a very less important point, okay? This point is more of an opinion than anything. But I personally believe that the adjectives or labels strong and now, by comparison, weak are wrong. They're, in fact, backwards. This is just an opinion, but I do want to point it out in case any of you go on to take any more, say, classes in logic, or you chat with a logician for some reason. They also might agree with my opinion here. That is, what we're calling strong induction, we should really call weak induction. Right? And so why is that? Well, here's the thinking. Under strong induction, as I just sort of showed you, this technique uses a larger inductive hypothesis. So, uses a larger hypothesis. And that's true, you're assuming more, which makes it seem like, oh, I have more to use. So it feels like you have more ability to prove things, but that's only because you have assumed more. So strong induction uses a larger hypothesis to prove the same conclusion as regular induction, to prove that the k+1 case is true. So because this technique has to assume more, logicians would say this is a weaker technique. Let me make a poor analogy here. Imagine you have two people who say they can build you a house. One person says, oh, I can build you a house and I use all these tools. I use drills and trucks and a whole bunch of tools. And the other person says, well, I can build you this house. I'm just going to use a hammer and nails. You might say that the second builder is stronger. She or he is much more capable of building the house because they don't need as many tools. That's what's sort of going on with this opinion here. Strong induction, what we call strong induction, is really in some sense weaker. It has to use more assumption to get the same result. Okay, but that second point in particular is not really worth paying attention to. I just always feel obligated to share it with my students. In math world and in comp sci land, whenever you talk about strong induction, this is what they mean. Your inductive hypothesis does not just include your previous step. It includes all previous steps. So it's a stronger hypothesis. Okay. All right, so maybe we should see an important example of this. Let's see. So here's where you're going to hear me going oh and but I've got to look through some notes. Okay, so here's a standard example of using strong induction. And I actually looked this up quite a bit, and a lot of comp sci courses like to use this example. So it's a bit outdated, but here you go. Prove that any amount of postage greater than or equal to 12 cents can be created using 4-cent and 5-cent stamps. Okay, so I don't use the post office that much, but I suspect you guys still largely appreciate what this example is trying to say. Right? It's trying to say you've got a 4-cent stamp and a 5-cent stamp, and you can use any number of those you want. And the claim is that you can create any amount of money, any amount of postage, that's 12 cents or more. So the statement, I'm going to say statement P of n is maybe the statement n cents of postage can be created or obtained or achieved using 4 and 5-cent stamps. And then the claim we're looking at is that P of n is true for all values of n greater than or equal to 12. Okay, so by the way, there are other values that you can get. Maybe I should comment on this in a different color, like in purple. This isn't saying these are the only ones you can get, but it does say that you can definitely get all of these. But you can also get 8 cents of postage by using 2 4-cent stamps. You can get 9 cents of postage by using 1 4-cent and 1 5-cent. You can get 10 cents of postage by using 2 5-cent stamps. And now the question is, can you get 11 cents? I think I'll let you guys think about 11. Okay, but the claim is, well, don't worry about 11. At 12 and beyond, you can get this. So let's prove this, maybe in orange, by induction. Proof. And we'll say by strong induction. So what does this proof by strong induction look like? Well, again, we have a base case. And our base case will be when n equals 12, right? For this one, the claim doesn't start at 0, it starts at 12. So what we want to show is that 12 can be created using multiples of 4 and 5, specifically using positive or non-negative multiples of 4 and 5. And this isn't too hard because we can write 12 is 3 4-cent stamps, so 3 times 4, and 0 5-cent stamps. So that claim is true. Okay, and now for our inductive step. And since this is strong induction, we're actually going to write this part a little bit different. Assume P of n is true for every n starting at our starting point, 12, and up to some number k. And then what we want to do, we want to show that P of k plus 1 is true. Okay, so here's where really, if you're doing this on your own, you would spend a lot of time relating the k plus 1 statement to the previous k maybe kth statement, k minus 1 statement, right? So this is where you should really pause the video and explore this relationship on your own. But okay, so let me just note, by our inductive hypothesis, P of k equals some number of 4-cent stamps plus some number of 5-cent stamps. Our inductive hypothesis actually tells us more. It tells us P of k minus 1 is 4 times some other number plus 5 times some other number. But for this particular one, I am going to focus on the previous one. And what I'm actually going to do is break this into cases. So case 1, let's say A is at least 1. Let's say for the kth, for k cents of postage, I had to use at least 1 4-cent stamp. Then, oh, sorry, I miswrote. So up ahead it says by our inductive hypothesis, k, right? K cents of postage can be written, or can be achieved using some 4-cent stamps and some 5-cent stamps. Sorry about that. So suppose that the k cents of postage can be written using at least 1 4-cent stamp and some other number of 5-cent stamps. Then this allows me to write k as 4 times a minus 1 plus 1 plus 5 times b. And so the reason I have to be a little more careful here is that I want to make sure this number right here, a minus 1, I want to make sure that's not negative, right? And that's why I really needed to break this up into a case. And so once I have this case on the ground, then it now follows that k plus 1 is my expression for k, so 4 times a minus 1 plus 5 times b, plus that extra 4 that I pulled out, and now plus my extra 1. Right, so maybe I'll highlight that 1. So this plus 1, I just tacked on this 1, and what we can see here is something is really nice is going to happen. Once we work out this arithmetic, we're going to get 4 times a minus 1 plus, that 4 plus 1 becomes a 5. And so I can write this as 4 times a minus 1 plus 5 times b plus 1. And look at what we've said here. If we can create k cents of postage using a 4-cent stamps and b 5-cent stamps, then in this case we can create k plus 1 cents of postage using a minus 1 4-cent stamps and b plus 1 5-cent stamps. Okay, so for case 1, I actually didn't use anything except that my statement was true at the previous case. So it's case 2 where the strong part of my hypothesis comes in. I'm going to assume that a isn't bigger than or equal to 1. That is, that I'm not using at least 1 4-cent stamp. I'm assuming that I'm using 0 4-cent stamps. And so now I get that k cents of postage can be created using a 4 cents and b 5-cent stamps. Well, I'm really just getting this. And here's also where I want to scroll back to the beginning of this question, where we said k, right, sorry, I assumed past, where we said k is bigger than 12. So we're going to use that assumption right there that I underlined twice. So I'm going to mention that here. So the value of k is bigger than 12, and we can work this out. This implies that b is bigger than or equal to 3. Okay. So now what I'm going to do is, oh, give me a second, sorry. So now what I'm going to do is just note that k plus 1 is equal to 4 cent stamps plus b minus 3, I'll write it this way, plus b minus 3 5-cent stamps. And let's see why this is. This is just me working out some math. This is equal to 16 plus 5b minus 15. So when you work out that math, you're just going to get 5b plus 1. And what did we know? That we assumed that k was equal to 4 times 0 plus 5b. So this was k. This guy was k. And so this finishes my proof. All right, so and so that's one sort of version here of doing a proof by induction, proof by strong induction, excuse me. And let me, excuse me, 1 second, sort of. All right, let's see. Right, and so I think, so, okay, sorry, I was getting a little confused in how I wanted to say things. Where did this use, where did this kind of use strong induction? It kind of used strong induction. I realize now that I kind of hid the way I presented it. The strong induction kind of got hidden, so I apologize. But it kind of used strong induction here when I went 3 less, right? If I only assume the previous case, then subtracting 3 may be problematic. Whereas up above, in case 1, I only went 1 less, so the previous case was okay. So that's sort of where this happens. Let me point you in the direction of what I think is a better strong induction example. Actually, I don't think that one was the best, so I apologize for wasting your time. But I'll say a better strong induction example of strong induction. Rather than work it out, I'll tell you where to find it. It's a good one. So here's the claim that 12 divides the expression n to the 4th minus n squared for every natural number bigger than, for every natural number, including 0. So the point about this one is that if you try this using regular induction, it's really natural to get stuck once you go from your previous case to your next case. So, so regular induction, regular / weak induction, get stuck. That's not to say you can't unstick it, but it takes more work to unstick it. So what happens is you assume 12 can divide k to the fourth minus k squared, and then you look at k plus 1 to the fourth minus k plus 1 squared, and you're trying to prove 12 can divide this thing. The problem is when you look at this, you do end up getting like a 12 times some stuff, and that's great. But in fact, you do end up getting, one of the terms you get is k to the fourth minus k squared, and that's great, right? Because that's your previous step. You know 12 divides that. But then you get some other stuff, and this other stuff, it's not clear that 12 divides this stuff when you write it all out. So you can create another proof that 12 always divides that stuff that I'm hiding from you, but it's another proof built inside of your already proof by induction. So what you can actually do is handle this by strong induction. And so let me point out where you can read up on this example. A great book called The Book of Proof. There's free copies of it online. This is by Dr. I forget his first name, I think. Let me look it up really quick. I think it's Hammock. Is that right? Sorry, let me type it up. Book of Proof. Yeah, Richard Hammock. So Dr. Hammock. So if you Google this, it's like the first one. And if you look at section 10.2, he talks about induction and strong induction, and he goes over this exact example. The one thing I would tell you to pay attention to in this example is note what he actually uses. The proof uses, I think, several previous statements. So what we're calling P of k, wait, I think he's going to use P of k minus 1 and P of k, and I think he goes back, if I'm not mistaken, I think he goes back to 5 statements, I think. Something like this. So he'll use these, something like this, to prove the next statement, that 12 divides the k plus 1 expression. But my point in bringing this up is it's actually not using full strong induction, right? Because he's not using all previous cases, just some amount of previous cases, more than one though, so it's stronger induction. Because of that, his base case will have to check the first 5 previous cases. Okay, so it's worth reading. This book is really, really well written and it's free. So I just want to point you to that example. That's a better example of strong induction in my opinion. Here is, though, what I think is the best example of strong induction. And it goes back to prime numbers. So the best example of strong induction concerns prime numbers. So this is actually a really, really good example. And so let me just have this prepared. Let me go. All right. So here's let's see. Okay, so here's the fact that we're going to prove. The claim: every natural number bigger than 1. So for every natural number, little n, bigger than 1, n is, I think I should say strictly bigger than 1, n is the product of prime numbers. So this is what I'd like to prove, and because this is a statement with a starting point, it would start at n equals 2, right? And it's a statement for infinitely many things. It's an ideal candidate for induction. It turns out we're going to prove this by strong induction. So proof using strong induction. So our base case is pretty simple. That's just when n is as small as it can be, so n equals 2. Well, in this case, 2 is a prime, and so is the product of primes. It's just 2, that's it. It's the product, if you will, of one prime. So the statement is true at n equals 2. And now, our inductive step. Our inductive step is to say, suppose the statement is true for all natural numbers, n bigger than 1, and up to and including some natural number k. We want to show the statement is true when n equals the next number, k plus 1. Alright, but how are we going to do this? Well, this actually turns out to be ridiculously easy with strong induction. Right, so here's what we're going to say. So case 1, n is already prime. Well, in this case, like our base case, n is the product of one prime number. So you're done, just like in our base case. So it's really case 2. That's where all the work is. Oh, I said n, sorry. I meant k plus 1. So case 2 says k plus 1 is not prime. And let's think about this. Let's go and negate our definition of prime number. Right? What does it mean to be prime? Well, you can think about it as if you're prime, the only numbers that divide you are 1 and yourself. So if you're not prime, some other numbers divide you. Our other definition of prime was you have exactly 2 divisors. So if you're not prime, then you have not exactly 2 divisors. And there's a couple different cases, right? You might have 1 divisor, in which case you're the number 1, but we said that wasn't happening because you're bigger than 1. So you would have more than 2 divisors. Okay, so in either case, this means, however we decode prime exactly, this means k plus 1 is equal to 2 numbers multiplied, where both of these numbers, neither one is 1, so a is bigger than 1, and neither one is k plus 1, right? They're both different. And here's where we get to appeal to strong induction. Look at what we have here. I'll just highlight these, just to be pedantic. the number a, which is a divisor of k plus 1, is less than k plus 1. So our strong inductive hypothesis applies to the number a. Since a is less than k plus 1, our inductive hypothesis applies to a and tells us that a is just a bunch of prime numbers multiplied, p1 times p2 dot 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 dot, all the way up to some number, I don't know, p sub l, I don't know. Similarly, the number b is less than k plus 1. And so our strong inductive hypothesis applies to the number b. Similarly, b is equal to a product of a bunch of primes, I'll call them q's, and I don't know how many there are, maybe there's m of them, where each pi and qi is prime. Okay, and now we're pretty much done, because now k plus 1 we assumed was some number a times some number b. Those had to be small numbers, so our strong inductive hypotheses apply to each of them, and so each one is a product of primes, and so now k plus 1 is a product of prime numbers. Right? It's a bunch of prime numbers p times a bunch of prime numbers q. And so the strong induction here was super useful, right in the part where I highlighted, because I don't know how much smaller than k the number a is. All I need to know, though, is that it's smaller, and so we assumed that the hypothesis was true for all smaller numbers, all numbers smaller than k plus 1, and similarly for b. So this result, every natural number is the product of prime numbers, you can prove pretty easily using strong induction. And I want to point out something. You should be saying, wait a minute, isn't this the fundamental theorem of arithmetic? That's what we talked about in my last upload. And the answer is yes. At least part of it. This was the main part of it. It is true, this was the part that we were really after, that every natural number is a product of primes, but really the full version of the fundamental theorem of arithmetic says every natural number is essentially a unique product of primes. There's only basically one way to write them as a product of primes. So to prove the full theorem, I'm required to need to show uniqueness. And I want to make a comment here. In my previous upload, so let me write this as a correction to the previous discussion or video, I said that the proof of the fundamental theorem of arithmetic was usually done in a group theory class, and that's not exactly true. I was just getting confused. There's a fundamental theorem of finitely generated abelian groups that uses this theorem or includes this theorem. But I think I said last time that usually we wait to prove this until the group theory class. That's not necessarily true. You might use this theorem as part of this group theory proof, but you certainly don't have to wait and see it. So let me just put a big X there. Right, so what I'd like to do with the rest of this video is go over proving the rest of this theorem. We've used strong induction to prove the first part of it. Everything can be written as a product of primes, and so now I just want to prove the remaining parts. So let me do that. So to show that every natural number bigger than 1 is and I'm going to put this in quotes a little, a unique product of prime numbers. We first prove a really nice little result called Euclid's lemma. And this is actually a really nice fact to know. It's also about prime numbers. So not Euclid lemma, Euclid's lemma. Here's what it says. It's actually not about prime numbers, so I'm going to state it a little more carefully. If the greatest common divisor of two numbers is 1, do I want to use A and B? Maybe I'll use different symbols. Yeah, that's... let me use a different symbol than B. I'm just thinking ahead. So if the greatest common divisor between two numbers A and C is 1, so if A and C are relatively prime, then whenever C divides A times B, it follows that this number C, C has to divide the number B. So the idea is, it's kind of intuitive, right? We definitely want to believe this. It says if you have two relatively prime numbers A and C, so they don't have any common factors except 1. And if you're told C divides A times another number, the thinking is, well, maybe C can't divide into A, so it's only got to divide into B. That's the thinking. And it turns out that thinking is right. And our proof is going to use what we talked about in the previous discussion. We're going to use Bézout's identity or lemma. So by Bézout's lemma, we know that the GCD of A and C, which I'm assuming to be 1, is a linear combination of A and C. So for some integers, x and y, that's actually the key step in this version of this. Okay, so if the greatest common divisor is 1, then 1 is a linear combination of these two expressions. So this all has to be true. And now what I'm going to do is multiply this expression, this equation, by the number b. So I'm going to write it in blue. Well, I'll highlight it in blue. So I'll get b times 1 equals b equals a times b times x plus c times b times y. So just to keep us focused on what I'm really want to pay attention to, I'll keep highlighting this in blue. Okay, and what are we assuming? So if C divides A times B, then C divides everything on the right-hand side of this equal sign. So, right, C divides this number, C divides this number, so C divides the whole thing. This implies C divides the left-hand side, which is to say, in other words, C divides B. And that was our conclusion. If C divides A times B, then C divides B. Okay, so we get as a corollary to this an immediate result, an important fact about prime numbers. So what I said above, what I called Euclid's lemma, is not about prime numbers exactly, it's about relatively prime numbers, right? I said if the GCD of A and C is 1, if A and C are relatively prime, then whenever C divides the product of A and B, it divides the other number, B. So think about this corollary. This is for prime numbers. Here's what it says. If P is prime and P divides a product of integers, then what can we say? So you should pause the video here to make sure that this makes sense. But what this tells us, if you've joined us after pausing, this tells us either P divides A or P divides B. Right, so why is this the corollary? I'll just sort of sketch this as to why this follows from Euclid's lemma. Well, here's what we would say. If, let's say, P doesn't divide A, then it has to be that the GCD of A and P is 1, and that's since P is prime. So Euclid's lemma now tells us, Euclid now tells us that P dividing A times B tells us P divides B. You could also say, okay, well, what if P didn't divide B? Then you would be forced to conclude that P divides A. So it turns out this corollary here is a key property of prime numbers. I want to point out this corollary is not true unless you know P is prime. Right? So like we can try a non-prime number. So let's just do a cautionary example, a warning example. It is absolutely true that 4 divides the product 3 times 8. But 4 does not divide 3, and... oh, sorry, that was a terrible example. I'm sorry. 4 does divide 8. Gosh, I'm sorry. Let me think of a better one. Sorry, I had the right thing in mind. It is absolutely true that 6 divides 3 times 8. But 6 does not divide 3, and 6 does not divide 8. And what's going on here is, well, 6 isn't prime, so we're not guaranteed to know this. Okay. So Euclid's lemma and this corollary about prime numbers are good things to see and know. I'll just point out that the proof for this went like this sort of chain of proofs we've been discussing. We actually started off with the division algorithm, and we didn't prove this. What I said about this algorithm was that it somehow, you can prove it using what's called the well-ordering principle, but we sort of took it as a fact. But then using the division algorithm, you can use Euclid's use of this, so Euclid's algorithm, we use that to prove Bézout's lemma, identity. And now we use this to get, this was a key part in Euclid's lemma. Okay, so that was just a little comment that Euclid's name appeared right in part of the proof for Bézout's lemma. How did we prove Bézout's lemma? Well, we did Euclid's algorithm backwards. That gives you Bézout's lemma. But then Bézout's lemma comes in and helps prove Euclid, another fact by Euclid. So Euclid helped prove something that helped prove something about Euclid. Okay. So why is this such a big deal? Now what we want to look at is, now I want to look at that fundamental theorem of arithmetic. And what it says is that every natural number bigger than 1 can be expressed in the following form as n equals some number of primes, so I'll say a1 prime 1s times some number of prime 2s and up to some other number. We'll stop it at r. Right. So the proof for this, again, I had said, misspoken and said, the proof has to wait. Proof doesn't have to wait. Part 1 of the proof is to just show every natural number bigger than 1 is the product of primes. And we did that at the start of this. We did this. This gets a check using strong induction. And so it's really part 2 that I want to finish this with. The second part of the proof needs to show there's basically only one way to write this, essentially. So what I mean is, the way we're going to do part 2 is I'm going to say, suppose the number n can be written as a bunch of primes p1, maybe more than one of them, times a bunch of primes p2, maybe more than another, and then times some other bunch of primes pr. But suppose this also equals a bunch of other primes, q1 and q2, and I don't know, I'll say ql. What we want to show is that each pi has to equal a qi, and then the exponents are equal. So I'll just sort of sketch how this goes. The idea is this, where each, sorry, I should say this, where each pi and qi are prime. So here's how the proof of this goes. Well, sorry, I don't know what's going on with my computer. We already know that by assumption prime p1 divides n. And that tells me prime p1 divides all of these q's. And here's where I'm going to use Euclid's lemma. This tells me that prime P1 has to divide one of these Q's. I'll say Qj. That's where I used Euclid's lemma. If P divides a product of numbers, it's got to divide one of them. And look here, I'm going to use the lemma again. If it divides a bunch of Qj's multiplied, it's got to divide one of the Qj's. So I used it here and here. But there's a problem with this. I said Q's, so Qj is prime. So the only things that divide Qj, right, is 1 or itself. However, since the p's are also prime, 1 is not a prime number. So we just learned that if p1 divides n, then p1 has to be one of these primes over here. And there's really nothing stopping me from saying, well, no, this is also true for p2. So really I could say for pi, if pi divides n, pi divides all these q's. By Euclid's lemma, it divides one of these q's. And so pi has to equal some qj. And so this tells me all the p's and q's are the same. You may have called them p's, I may have called them q's, but they were secretly the same primes. The only difference is they may have a different order. And then it's not too hard from here to show that the powers have to be the same. So I'm going to go ahead and put a proof square here to say, well, we're done proving this. We're pretty much done proving it. Right? So all I'm saying here, right, is something pretty believable, that if, for example, you write your favorite number, I don't know, 24, I write this as 2 cubed times 3. And you write this as 3 times 2 cubed. Well, you still had to use 3 2's just like me. So there's your P, that's my P1, that's my P2, and I have 3 P1s. And you're going to say, oh, well, this is Q1, and I have 3 Q2's. So what you called Q2, I called P1, and what you called Q1, I called P2. That's the only difference. So what we have here is, by a combination of strong induction and Euclid's lemma, we actually have the fundamental theorem of arithmetic. The last thing I just want to mention to close this video is just some fun mysteries about primes. So there's a lot of these. So let me go back to my notes. Let me look here. So perhaps one of the more famous ones, where did it go? Is Goldbach's conjecture. So this is a famous open mystery. And here's what it says. Every, I believe it's even integer greater than 2, can be expressed as the sum of 2 primes. So every even integer greater than or equal to 2 is equal to P1 plus P2, where P1 and P2 are primes. No one knows if this is true yet, although it's been proved for, I think billions of even integers. They found a way to write this, right? So oops, excuse me. So for example, you know, well, 4 is just the prime 2 plus the prime 2, and 12. Let's think about if we can do 12. Sure, the prime 5 plus the prime 7. And it seems to be true for all other even integers, but nobody really knows. There's a lot of great videos and resources out there about something called the Riemann hypothesis, which is, let me put this here. So I won't be able to state this simply, but this relates prime numbers to this amazing expression, something called the Riemann zeta function. And the Riemann hypothesis is about this zeta function, about it can only spit out the output 0 at certain places. And it turns out that knowing this fact, right, being able to prove that this zeta function can only spit out 0 at these conjectured places actually helps you understand how prime numbers work. So everything I'm writing down here is sort of a mystery. We really don't know if the Riemann hypothesis is true. We don't know if this part is true. We know that the zeta function is related to prime numbers, but we don't know this underlying part. Another sort of fun mystery about prime numbers is the twin prime conjecture. So I'll just say twin primes. So what is a twin prime? A twin prime is a pair of primes that are as close as they can be. So what do I mean by a pair of primes that are as close as they can be? They can't be 1 apart unless you happen to be talking about the numbers 2 and 3, but they're 2 apart. So a pair of primes, say P1 and P2, where let's say the second one, P2, is just P1 plus 2. So these are called twin primes, right? So some examples of twin primes are 3 and 5. These are twin primes. What else are twin primes? 5 and 7. You get some sort of interesting ones like 17 and 19, maybe is a little more interesting. And so the question is, how many twin primes are there? And the answer is, we don't know. The twin prime conjecture says there's probably infinitely many, but we actually don't know this. In fact, I think very recent work, I believe it was 2012, 2014, there was some sudden activity about the twin prime conjecture from an unexpected source. Somebody who was not being paid to research mathematics, but was sort of researching it on their own and found a new way to sort of think about this conjecture. Okay, so these were just some 3 quick little mysteries about prime numbers. And the reason I like to conclude this discussion on this note is that now I've put in a fair amount of work, and you guys have too, just trying to follow along to a video like this, of trying to understand this fundamental theorem of arithmetic. Let me scroll back up to where we stated. And again, the fundamental theorem of arithmetic, try not to get lost in my blue symbols here, it's really just saying that the prime numbers are your building blocks for all other numbers. And so they play a really, really important role, right? And so it's really strange that there's so much about prime numbers, like I just mentioned these 3 mysteries, that we don't know. Prime numbers are so important and crucial to arithmetic, and yet there's so much about them that we aren't sure of. They appear to have structure, but not really. in some sense they become less and less common, right? That was what I mentioned in our previous video. But if the twin prime conjecture is true, well then there's infinitely many pairs of them that are really close together, right? So maybe in some sense they're not less and less common. So primes are kind of mysterious, and they shouldn't be. Alright guys, I hope you're doing well. I'll talk to you another time.